Okay, so what we're going to do today for lab is, as I mentioned before, we don't officially sort of go over all that kind of intro chemistry type stuff like sig figs and measurements and density and all that. It is in your book, it kind of like a pre-chapter. As I mentioned, it is sort of a pre-chapter in your book. You are responsible for that material. It is the subject of the study assignment for today, which is study assignment A. And we'll talk a little bit about that in a second. Reminder that to find the study assignments, they actually come after the very last experiment. So I think it's like experiment 14 or whatever it is, kinetics. After that, in your manual is where you'll find the study assignments. Yeah. And by the way, for future reference, after the study assignments, you'll find some tables that we will use in some experiments down the road as well. So there'll be some tables after the study assignments of some information you need. So there should be the study assignments to come, I believe, right after perhaps experiment 14, the kinetics experiment. And there's like study assignment A through, I don't know, whatever letter in the alphabet it goes to. But we'll do a number of those. They essentially are worksheets, sort of dry material with no real hands-on experiments. So we're going to kind of go over that information again, just to make sure everybody's on the same page. Hopefully, most of it is reviewed for you, I hope. If not, then hopefully you'll be okay. And you can also reference, like I said, the kind of pre-chapter where all this will be. This material you will be perhaps tested on during exam 2. Yeah, so this kind of sig figs, density, that type of stuff will be maybe part of exam 2. All right, so let's just get into it. And like I said, afterwards, we'll talk about the study assignment A when it's due. And then we'll also talk about the experiment on Thursday, which is our first sort of formal experiment. And then we'll get out of here, I hope. All right. So essentially, we're going to talk about sort of the, I guess, pre-chapter, we'll call it, in your book. All right, so might as well just start with what everybody hopefully knows, which is measurements, right? And again, I don't really have any set notes on this, so I'm just going to kind of go off the top of my head and see what flies here. So obviously, when we take measurements, you should always have a number and a unit. And the unit obviously is really important because it does tell people, obviously, and I'm recording this, so it'll be up there if you want to watch it later and stuff like that. Yeah. So the unit obviously tells people what the number means. So obviously, if we had a number like 300, who knows really what that means? There's no point of reference for it. I could have $300, which would be great. I could have 300 pennies, still great. 300 apples, that's a lot of apples to make some apple pie or something like that, but that is a lot going on there. So we do need to have some type of unit always associated with a number when you take a measurement. And as you may be familiar with, there's really kind of two types of units that we sort of come across. There is what is sometimes referred to as the English units or the US units, and also the metric units. And for a long time, obviously, we use sort of the English US sort of system. Pretty much everybody else uses metric system, and that could cause problems, obviously. So around the 60s, 1960, they came up with what is referred to as the SI system of units, and that's the International System of Units. For all intents purposes, it's kind of metric-y, I would say, kind of one, and it's basically based off the metric system. When we talk about units, it's important to understand what they represent. So, for example, if we have grams, right, that is a mass, I hope. By the way, there is a difference, as hopefully you know, right, between mass and weight. Weight takes into account the force of gravity, right, and mass does not. And when we do weigh something in the laboratory, we are getting the mass of it. The balances are adjusted to take out sort of the force of gravity, and we are actually measuring the mass of an object when we do so. We have something like liters, right? That's a volume, right? We have something like meters, that's a length. Seconds is a time. And everybody's favorite unit, Kelvin, is obviously a temperature, right? So it's really important to know exactly sort of what those units represent. So you don't say like, my solid weighed 43 milliliters, right? And that's a volume, right? So when we do take measurements, there's really two types of observations that we come across. There is qualitative and quantitative. And qualitative observations are sort of like general observations about something. It is not really measurements or anything like that. For example, if you take 200B, you'll do some experiments that are known as qualitative analysis. And qualitative is really just more basic, sort of basic observations, no measurements, like it turned purple, we got a solid, there was gas that came out, that type of stuff. And like I said, if you take 200B, you'll do experiments which are qualitative analysis, and you basically do experiments where you don't weigh out anything. You just put like, 40 drops in, or a few drops of this, a few drops of that. It's not important to weigh it out. You're really just looking for observations of what happens when you add these reagents. Now, quantitative is all about measurements, right? And when you take measurements, you get actual values, you get actual numbers, and that's what we do. Obviously, most of the time in the experiments that we do, we take some type of quantitative measurement. We also should take some qualitative measurements as well, or observations, really, qualitative observations as well of what's going on besides just the numbers. Now, when we do take a measurement, there's always some degree of uncertainty associated with any type of measurement. And that degree of uncertainty is based on the equipment that you use. So for example, if you had like a ruler, and we wanted to measure, say, this arrow here. When you look at any measuring device, there's usually two types of numbers that you come across. There are large markings and there are small markings. And large markings usually have actual numbers on them. So the difference between the large markings in this case is 1 centimeter. Then the small markings are the markings that are between the larger ones. And when you count them, you want to count them correctly. You always start counting after the last large marking. So you start counting there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And you stop at the next large marking, which would be 10 in this case. So there are 10 small markings in between the large markings. So if you take 1 divided by 10, that tells you that each of the smaller markings in this case is 0.1 of a centimeter. So this would be like 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, all the way up to 2, obviously, in this case. So when you have that all worked out, and you should always look at the scaling on whatever you're using to make sure you do record it properly. There should always be some numbers that really nobody disagrees upon, everybody sort of agrees upon. And I would think everybody should agree my arrow is at least 1.4. And those would be numbers that we would want to record in our measurement. These are sometimes referred to as all the certain numbers. But we could clearly see that my arrow is not exactly at 1.4. It's not exactly really at 1.5 either. It's somewhere in between. And that's where the uncertainty in this measurement comes from. And for example, you may look at it and go, well, kind of looks maybe halfway between those two markings. And you would record perhaps a 5 and obviously the units with it. And this would be what is referred to as the first uncertain number. And whenever you take a measurement, you should always record all the certain numbers and that first uncertain number. And that uncertain number is where really the uncertainty in this measurement, or error sort of in this measurement, is at. Somebody else may look at it and go, I don't think it's halfway. I think it's just a little bit before halfway, may record a 4, right? Somebody else may think, well, maybe it's a little further. and maybe record a different number. So we're talking about kind of plus or minus that uncertain digit. Now, when we take a measurement, it's really important to do that because when you do that, you are actually, when you record all the certain numbers plus the first uncertain number, that is really what significant figures are. Yeah. And that means that this number here should have 3 significant figures in this particular case. And again, significant figures come from measurements, which have some uncertainty in it, and you want to record always all the certain numbers plus the first uncertain number. Any question on that there? Speaking of that, obviously we could have different measuring devices, and maybe we have a terribly drawn graduated-ish cylinder, and we'll go down. And let's just say these are milliliters, and we have some type of liquid in there, right? I'm going that way. By the way, when we measure a liquid in a glass cylinder, you typically will see a curvature of the liquid, maybe not that dramatic, but that curvature of the liquid will look something like that. That's known as the meniscus, right? And you typically, if it is a U-shaped meniscus, read from the bottom of the meniscus. Sometimes it's easier to see than in other cases. You have a really big opening, very hard to see sometimes. And if you have a smaller opening, a little bit easier to see. That happens, as you may know, and we'll also talk about, because the attractive forces between the liquid and the glass are actually stronger than the attractive force between the liquid and itself. So what happens on the sides where it's in contact with the glass, through capillary action, starts rising and creates that volume kind of going up on the bottom. That's why, by the way, we read from the bottom of the meniscus where it's not touching the glass, because that's truly where the volume is if it didn't have that interaction drawing it up on the sides of the glass container. Most things have a meniscus that looks like that. Some things actually have a reverse meniscus, if you will. It actually goes like this, and you would actually read from the top of the meniscus. Mercury, for example, does that. Mercury is actually more attracted to itself than the glass container. It actually comes in on itself. So very rarely will you see a meniscus like that. Most of the time it's going to be like that. But some things can go in the opposite direction. You probably won't see mercury because they've taken it out of pretty much all labs around town. So you don't see too much of that going around anymore. But it can actually go in the other way. So we'll do the same thing here. If we take our large markings, and that is 10 and that is 20. So that is 10 milliliters. Again, counting our smaller markings here between the two. Again, starting counting here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, here we have 10 markings between our large markings. That means if we divide those two, each of our small markings in this case is 1 milliliter. That'll be 11, 12, 13, 14, 15, 16, 17, 18, and 19, and 20. So now if we were going to record this, again, taking bottomish of the meniscus there, we should see it as at least 15. Again, not exactly at 15. Maybe you feel it's a little less than half in this case. Maybe you record a 3, and milliliters, again, are certain numbers and our first uncertain number in this case. And giving this also 3 significant figures with the uncertainty in the last digit there of the 3. Any questions on that there? Now, again, it's really important, even if you're using the same type of glassware, the scaling may not be the same. So if you had maybe another graduated cylinder-ish, working even worse than the first one I bought it from. Now, if we come somewhere like that. Now, if we look at the large markings on this one, we got 10 and 20. That is still 10 milliliters. But the difference here, though, when we look at between our markings, we have 1, 2, 3, 4, and only 5 markings in this case. And that means that if we take that divided by 5, each of the small markings in this case actually equals 2 milliliters. So this would be 12, 14, 16, 18. So now when we come to take a reading on this particular scale, what is between 16 and 18? That is number What number comes between that? 17 is actually the best you could do on this particular scale. And that is because on this particular scale, you have no idea where 16 stops, where 17 starts. There's not enough room to sort of visualize that happening. That would mean, by the way, this would have how many significant figures? This would have 2 significant figures. The uncertain number would be the 7 in this case, yeah? So you're basically saying, I think it's 17, somewhere between 17, 18, 16, somewhere in that ballpark. That's a pretty big range of errors. So on this one, you could actually only go to the whole number. Now, in general, you could usually go to one more place to the right of the smallest marking, not all the time, as you can see here. So if you're not really sure in a case, really how far you should take the reading, but you are fairly confident in figuring out what the small markings represent, you can very simply take the small markings, divide it by 2, and this will give you something like plus or minus 0.05 centimeters. That is 2 decimal places. That is how far you should take the reading to. That's sometimes referred to as the tolerance or precision of the thing that sometimes is included in a measurement. We don't do it here, but sometimes people include that. Same thing here. Smallest marking is 1 divided by 2 gets you plus or minus 0.5 milliliters. That is 1 decimal place, and that's exactly where we should take it to. Even works on a guy like this here. Divide that by 2 gets you plus or minus 1 milliliter, which is exactly where we took this reading to. So if you're fairly confident on the small marking, but not really confident how far you should take it to, you can just take the smallest marking divided by 2, however many decimal places or wherever that ends up to is really how far you should take the reading to. Any questions on that there? By the way, other things that people, maybe mess up on. Let's say we go back to the ruler we started with. And let's say we're taking a measurement like dead on to that line right there. So clear is the same ruler we had previously where our large markings were 1 centimeter. Our small markings here is 0.1 centimeter. And obviously that would be 1.1, 1.2, 1.3, 1.4. So if we want to record this, 1.4 centimeters, 1.40 centimeters, 1.400000 centimeters. Is there any difference in the way you record it? There is. So the difference, right, is actually in the number of significant figures, right? So if I were to, for example, look at this one, right, that basically has how many significant figures? That has 2 significant figures. The uncertain digit here is the 4, right? That's the last significant figure. So basically what we're saying when we take this measurement is I think it's 1.4 centimeters, but maybe it's like 1.5, maybe it's like 1.3. We're basically saying if I record that measurement that I think the error on this device is, somewhere in that region. That's a pretty big error, right? Now, if I take this guy, this has how many significant figures? It does have 3 significant figures. Uncertain number is the 0, right? So what you're saying when you take this measurement, I think it's 1.40, but maybe it's 1.41, maybe it's 1.39. We're now talking about an error of here, right? And that is pretty much more what we see on our scale here, and we can actually measure to on our scale here, and that's why we should have that 0. So if you do this move here where you just drop off a 0, you basically made your measurement pretty crappy, yes? Then it should be based on that equipment that you're using. You should be able to do much better than you did because you made the error now move to the left a little bit and make it a much worse measurement. By the way, would this be any better adding some way extra zeros? It is not better because you did the opposite in this case. You made your measurement way better than you ever could on that piece of equipment. There's no way you could do that. So you do want to make sure that if you end up exactly on a number, that you maybe need to add a 0 to maintain the proper number of significant figures. So you do not make your measurement worse. As you know, people seem to always like to get right on the number there, always 100% of the time. and stuff. By the way, if you're measuring something that is digital, you should record all the numbers that are on there because they're all important. And that is how many significant figures, whatever the digital display basically tells you. That happens a lot when people weigh things out. Oh yeah, I weighed it out exactly to 12.000. Perfect. I stood there for an hour, scooping every little crystal on there and stuff like that. All right, any questions on how to take measurements? Yeah. Speaking of measurements and taking things, for example, in the laboratory, uh, we look at two things sometimes, right? We look at being accurate and precision. And if you're accurate, that means that you are close to the true value. And precision has to do with how close a set of numbers are to one another. So a lot of times when we look at precision, we look at like reproducibility of an experiment, which is why sometimes you do multiple trials of an experiment to see if you get the same results over and over. Accuracy, we look at how close it is to the real value or the true value that you're shooting for. We oftentimes will calculate percent error when we're doing accuracy, and that is your experimental value minus the true value divided by the true value times 100%. With precision, sometimes we do standard deviation, percent standard deviation, and stuff like that. Not too much here. We don't do that, but we do percent error here. But one looks at the other. So the common example of this is if we were shooting darts at a dartboard, right? The goal is to hit the bullseye in the middle. So if I throw 3 darts and I hit here, and hit the poor guy sitting there with my dart, am I very precise? No. Am I very accurate? No, and I hopefully didn't injure that person too badly by missing the dartboard completely. So I pick up my dignity and my darts, and I try again here. And I go double or nothing. You shouldn't bet or do anything like that. Friendly wager of no money. We will shoot the darts right there, and we line them all right there. Am I precise? I am. Am I accurate? I am not. I'm precisely not accurate, right? And that brings up a really good point that you could redo an experiment multiple times the wrong way and be really great at doing it the wrong way, the same way every time, but you're not getting the right answer, right? So the idea here is we definitely want to have something that's repeatable, but perhaps we might want some accuracy in that. So I did better. I didn't kill anybody there with a dart this time. That's good. So I go triple or nothing. Again, friendly wager of no money, of course. All right, and we shoot them there, and I go boom, boom, boom. Am I precise? Am I accurate? I am. I'm both, right? So that's really the goal when you do experiments, right? Is you want to be accurate, right? And you also want to be precise. So you want to be able to reproduce your experiment multiple times, and you want to really get the same result multiple times, and hopefully that same result is the true result and the result that you're looking for. Any questions on that there? All right, so since we've been talking about sig figs, obviously here, let's just roll through all that fine sig fig stuff, right? All right, so when counting sig figs, first rule there, right, is any non-zero is significant, right? So you got 4, 2, 3. We always start counting left to right when we look at a number, and we always start counting when we hit the first non-zero. So all these would be significant, so 3 significant figures. We have zeros, which gives everybody a tough time. We have leading zeros, and those are not significant. So 0.000112. Again, we would not start counting until we hit the 1, and then the 1 is significant and the 2 is significant. So this would be 3 significant figures for this particular one in this case. We have what are sometimes called trapped zeros or captive zeros. Those are significant, and those are zeros that are trapped between non-zero numbers like 404, 04. Why not? And here we start counting here. It's significant because it's trapped, significant because it's trapped, and significant. And that would give me 5 significant figures. In this case, everybody would be significant. And now the zero that people have trouble with, which is the trailing zero, right? And that may or may not be significant, right? And what determines whether or not the zeros at the end are significant is if there is a decimal point written in the number, then it's going to be significant. It cannot just be assumed to be there. It actually has to be written in the number. So if you had 600 like so, starting count here, that would be significant. These would not be significant because there is no decimal point written. This would have one significant figure, which means the uncertainty would lie where in this number? Which one's the uncertain number? You have a choice of really two numbers in this case, right? A 6 or a 0. Which one's the uncertain number? I think I heard kind of zeros. It's actually the 6 is the only significant figure and uncertain number here. So this is a really crappy measurement because basically you're saying, I think it's 600, but hey, maybe it's 700 or maybe it's like 500, right? That's a lot of room for error between there, right? So it's not the greatest measurement that happened in that case. Now, if I lay me up a decimal at the end, how many does it have now? It has 3 significant figures. The uncertain in this case would actually be the 0 at the end, yeah? And this is a much better measurement because basically what you're saying is I think it's 600, but maybe it's like 601, maybe it's 599. The error lies way over here, and that's way better measurement, obviously, than the first one in that case. So um, brings up 2 points. It does have to have a decimal point in it for it to be significant at the end. And again, the uncertain digit or the estimated digit in a measurement may not always be the last number written, but it should always be the last significant figure that's in that number. So whichever one's the last significant figure in that number is the uncertain or estimated digit. Any questions on that there? So, I got like 0.000400321000300 centimeters. Don't ask me how I made that measurement. How many significant figures does this one have? I have no idea. I was just really writing. So let's get there together. So going left to right, we're definitely not counting right here, right, is where we're going to first start counting. So now we run into some trap zeros. So those are all good, right? So those are significant. Non-zeros are significant. These technically are still trap zeros, right? So those are good. That's good. Now we have these zeros at the end. Are they significant? They are because the decimal point is way over here. So I think you said 12. I would maybe agree with you on that. I think that looks right, right? So again, it's also a good reminder that the decimal point does not need to be near the actual zeros at the end. It's got to be anywhere in that number, and that will make those zeros at the end. Now, sometimes people will go, hey, why aren't these zeros that come after a decimal point significant? Yeah, because we really haven't started counting yet, right? We haven't hit the first non-zero number, and that left to right is right here, and that's where we start counting. So since we did not hit the very first non-zero number, we don't count those. Those are now still considered leading zeros into it. And sometimes people think, well, it's after a decimal point, it should be significant as well. Any questions on funds and sig figs there? Let's talk a little bit about scientific notation, which is important. When you write something in scientific notation, we use scientific notation for handling really large numbers and really small numbers. And it should have this form, n times 10 to the n. That is a number between 1 and 10. It should not be 10, it should not be 20, but it can be 1, but it can't be less than 1. And this is either a positive or a negative number, depending on which way you need to move it to get to a number between 1 and 10. So if you had 423, we would assume the decimal points here, 1 place, 2 places, 4.23 times 10 to the 2. We move the decimal place to the left. It's a positive exponent. Large numbers have positive exponents. If you have this, we got to go 1 place, 2 places, 3 places. 4.321 times 10 to the minus 3. We have a negative exponent because it's a small number, we move to the right. Why did I keep all these numbers here? Because when we look at the original number here, how many significant figures does it have? This one has 4. Yeah, it has 4 significant figures. These guys right there, yeah. When you write a number in scientific notation, all the numbers that come before the times 10 part, so all these numbers are always significant. So when I write it in scientific notation like that, 4.321, I have 4 significant figures, which is the same sig figs I had in my decimal form. And you really should not try to lose sig figs as you go back and forth. That's also why here this had 3 significant figures. We have 3 numbers before the times 10 part, which means we have 3 significant figures in scientific notation. So we should not lose anything. Now, there is a case where the only way, for example, that you may be able to give an answer to the right number of significant figures is to write it in scientific notation. So there may be no other way to do it other than scientific notation. And that's why scientific notation is kind of nice because, frankly, let's just say I had this for my answer, and that would be 2 significant figures. But let's just say, for example, I needed 4 significant figures. Well, I could just add a couple of zeros, and now I have 4 significant figures. So you could almost control the number of significant figures when you write a number in scientific notation. And then again, like I said, sometimes that's the only way you can kind of get it to the right number of significant figures. So do you have to write everything in scientific notation? The answer is no, unless it tells you to do so. But if you want to, you can, but you don't have to write everything or give every answer in scientific notation. Probably more importantly about scientific notation is, I would say, calculator, as we think we maybe talked about during doing some of those calculations in the earlier chapter. Remember that when you use your calculator in scientific notation, you definitely want to make sure you use your exponent buttons. So again, for most people, there's an EE button, there's an EXP button, and some of the newer ones have a 10 to the n, or maybe times 10 to the n. And that usually will have a little will action happening on it. I would say most of the time these are two-tone in color. Has like a main color and a side color that's a little bit different, like green and white or blue and white type of calculators. And also another important button, again, a reminder, is I call it negative button, but change of sign button. Usually on most calculators looks like that, or this. You do not want to use your subtract button, by the way, when you do that. So if you have these buttons here, you don't have to be super careful when you use your calculator. You could kind of be sloppy and punch it in, you'll be okay, because they're programmed good in that sense, right? So if we have a number like 6.25 times 10 to the minus 6, and again, we wanted to punch that in properly into our calculator, you should go 6.25. You should hit that exponent button. And when you do so on your calculator, probably go 6.25, put an E, or it may go 6.25, pop up a couple of zeros, maybe a very small times 10. When you actually hit this button, as we might have talked about previously, that represents the times 10 part, which means you should not use the multiplication button. You should not, by the way, be using anything like the inverse log or shift log button, because you definitely will get the wrong answer probably in a lot of cases. What is left to actually punch in there is just the exponent part. So you want to hit your negative button and 6, and this will go -6, this will go negative, and that will become a 6. And that is the proper way to punch a number in scientific notation into your calculator. Now, if you got one of these two-tone ones here with both of these sort of buttons, you basically do the same thing, but the way those calculators are historically sort of programmed is, I won't say wrong, but you have to actually put parentheses around each number, otherwise your calculator would do the wrong math. So what you would have to do if you have this buttons here is you would actually have to open a parentheses, just like everything else, 6.25, you're going to hit your exponent button, and what it will show on your screen is 6.25, will pop a 10 times 10, you'll have a little blinking cursor up on top of the 10. At this point, you can do the rest just like normal, hit the negative button and 6. It will go 6.25 times 10 to the minus 6. you will then have the little blinking cursor to the right of the 6. The problem is your cursor is way up on top, which means in my experience, if you just try to close the parentheses at this point, it will try to close it like this. 6.25 times 10 to the minus 6. You have a really small parentheses up on top. And a lot of calculators, you'll get like an error that will happen. So this is where your will comes into play if you have a will. You usually do on this calculator. You take the will and you actually press the right-hand side of the will. That will bring your cursor down to a normal size cursor. And at this point, you can then close your parentheses. And now you will have your number there. Obviously, it's a lot of steps just written out step by step, but you will have basically your number in scientific notation. So you do have to parenthesis up every number in scientific notation if you have that type of calculator. If you have the other one, again, you could kind of not have to worry about the parentheses, but it works fine once you understand how to do it. Probably most important because most people don't know how to punch it in properly into their calculators. Any questions on that there? So if we did something like, 7.25 times 10 to the minus 11, and we divide it by 1.3, just write it out how you should punch it in. You go 7.25 and hit your exponent button. You can hit your negative button, and 11, you can obviously hit your divide button. 1.3, once again, exponent button on the next one. This is a positive exponent, so just 29 and equals. If you have the other type of calculator, you got to open a parentheses, 7.25, your exponent button, your negative button, and 11, your will button, close your parentheses, divide, open parentheses, 1.3, exponent button, no negative, 29, will one more time for good measure, and close the parentheses. That was a lot of writing right there. So either way there, this should get you, hopefully, to there. And if you do all that on your calculator, or at least on my calculator, your calculator may be slightly different. The little display is going to show me a mine 5.5769 2308 E minus 40. Yeah. So that's what I got on my calculator. Again, yours may look a little different at the end. Instead of E minus 40, you may have times 10 to the minus 40. Or in some calculators, they may just even put a space and minus 40. Like there'll be like a space between those numbers. Yeah.
So I did the top one.
Yeah.
And then I think I got negative 40 close.
Yeah.
But then I either did it with parentheses or without, but I ended up getting negative 59. Like what? No, why that?
I don't know, but this, I'll do it one more time just to make sure, but you should end up with this answer, I would think. So it may just be maybe you hit multiplication or miss something on that. Yeah. I got 40. Maybe I got 40. Yeah, minus 40. So it maybe, you have the 5.57 to the minus 39. Yeah, no, it's got to be something the way you're punching in. It shouldn't come that way. We'll take a look at it at the end if you want. Yeah, and just double check. But you should get that because if you had minus 39 and it's still this number, the decimal should move. Technically speaking. And so it should be yeah. Yeah, so we're gonna talk about it right now. So that's what you have, but basically whatever you have on your screen there, which should hopefully be this number, you do want to give it to the proper number signifiers, which we'll talk about the rules here one more time in a second, just to remind it. But reason I put what I have on my screen is because it is a very common thing that people will just put the front number and not the back number, yeah, and forget about the times 10 part and just kind of just put the front number. So you want to make sure that you don't forget the exponent part of your answer. Also, when you see E on here, That is not the way to give it as your answer. You should not use E when you're writing scientific notation, even though we use it like in computers and stuff to put those things in. You should give your answer in this case as 5.6 times 10 to the minus 40 in this case. And that is based off the sig fig rules of what we're doing here, which is dividing. So if you're having some issues on getting that number, you're not sure where your exponent button is, at some point, just come see me and we'll find it together and we'll work it out for you on your calculator and stuff. But let's talk about the rules of calculations with significant figures. And we really do two types of things, right? We multiply or divide. And as we did in this last example, if we multiply or divide, our answer should have the same number of sig figs as the number with the least number of significant figures. So if we took 425 times 0.11, this has 3 significant figures, this has 2 significant figures. Our answer when we're done should have 2 significant figures, and that's how we did on this last one here. This, because the scientific notation, has 3 significant figures. This has 2 significant figures, so our answer should end up with 2 significant figures. And again, in scientific notation, that is our 2 significant figures. Now, if you're adding or subtracting, it is different. And if you're adding or subtracting, you're looking at decimal places, not significant figures. And it is the smallest number of decimal places. So if you took 4.11 plus 2.05 plus 1.2, try without the calculator. Let's try our best here. A little college try, they call that. 427. Yeah. So here we're looking at decimal places. This has 3 decimal places. This has 2 decimal places. This has 1 decimal place, which means our answer should come to the 3. We do need to do some rounding, right? So we look at this, which is a 6. So we do round up, and we do end up with 7.4 here as our answer. 7.4 has 1 decimal place, but it has how many significant figures? 2. And that's important if you're going to take that 7.4 and then go use it in another calculation, right? So you want to make sure that you keep track of those things. And if you're multiple sort of doing calculations, you got to keep track of it. So if you did 423 times 0.11 divided by 468.99, the first thing we would do would be multiplying. And here we look at sig figs, which is 3 sig figs, 2 sig figs. That means technically when we get our answer for the top, it should have 2 significant figures. Then the last thing we're going to do is take the 2 significant figures and divide it by our bottom number, which has 5 significant figures. And that means our answer should end up with 2 significant figures. So you do need to keep track of your significant figures throughout your calculation. Usually it's the last calculation that will determine where you end up, but previous calculations also help you determine it at the end. So you got to keep track of it. You should also not do any extreme rounding during calculation, especially if you're doing multiple steps with those numbers. You should keep a few extra significant figures. They sometimes are digits, a few extra digits. They call it guard digits sometimes people a little line over where it should end, and they keep a couple of extra digits along the way. And you really should try not to round to the very end. At the very end, you should clean it up. Again, if you round a little bit along the way here and then a little bit along the way here and here, you're really just moving yourself further and further away from the right answer. So you want to avoid those rounding along the way. Any questions on that there? Speaking of rounding, no crazy rounding, right? So if I have 13,333 and I wanted 2 sig figs, what is the answer? 13? Maybe. No. How about 13,000? How many significant figures does this one have? How many significant figures does this one have? So they have the right sig figs, right? But we definitely would not want to use 13 because let's just take an example that happens daily. Let's say I owed you $13,000. 13,333 to be exact. I don't want to cheat you out of any money there. And I go, hey, I'm going to pay you two significant figures. Here's 13 bucks. I'm not going to make it out of the door, probably, right? Or the room. Well, maybe I will. You look friendly out there. So clearly, there's a very big difference, right, between $13 and $13,333. So we never want to round in an effort to get the proper number of significant figures that changes the meaning of the number, right? Now, 13,000 written that way has two significant figures, 13,000, 13,333, pretty much the same number. We didn't change it. Maybe I get the $333 teacher discount. And I'm okay in that sense. So you do want to be careful. Sometimes people try to go for the sig figs, which you should, but they do this kind of like extreme rounding that they change the meaning of numbers. So you never really want them to do that. Any questions on calculations, sig figs? Yeah. If you did, say it again. Okay. Yeah. So it does depend. It does depend on the situation. So let's talk a little about what that situation would be. So there's two types of numbers. There's measured numbers, right? And measured numbers basically have sig figs, right? And those are ones you get from a measurement. Then there's actually exact numbers, right? And exact numbers are ones that are either counted or a definition, right? And definition means like 12 inches equals 1 foot, right? And exact numbers actually have unlimited sig figs, right? And what that means is if you come across an exact number, you actually would ignore his contribution. You don't have to worry about it. And you just look at the ones that are more measured. So it does depend if we had units, for example. Let's just say that 2 was an actual measured value, right? So maybe you didn't have the greatest thing to measure it with, but it was like, 2 grams was a measured one. You would use it, for example, right? Now, if you were doing like an average, for example, you had maybe had more numbers on top, like you had a bunch of numbers and you were dividing it by like 2, right, for like an average, that would be considered more of an exact number and you wouldn't look at that. So it does depend on the situation of what that number is and then whether it's a sort of an exact number or a measured number. So if that one significant figure is an actual measured number on the bottom, then you would look at it and you would get the answer to, you would round up in that case to 2. If you are that 2 is just more like an exact number, you would actually keep it at 1.8 based on the top number only. Yeah. Other questions? So let's talk a little about as well equalities and dimensional analysis and conversion factors, which obviously is really important way to show your work. So for example, any type of thing like this, 12 inches is 1 foot. This is what is known as an equality. And an equality basically is two values that are on different units, but they represent the same amount. So 12 inches is the same distance or length as 1 foot, basically, right? And same thing if you had 100 pennies, it's the same amount of money as $1. So they represent the same amount. From any equality, as you may know, you can write two conversion factors from it. And conversion factors are basically just fractions where you put one of the values up on top and the other on the bottom, or the other value up on top and the other basically on the bottom. And when we use conversion factors, we basically use it when we're doing dimensional analysis. Dimensional analysis is the way that in chemistry, they basically want you to show your work most of the time. And basically dimensional analysis is using conversion factors. And the idea of it is a very simple idea. Let's just say we had 5 of unit A equals 2 of unit B, right? And let's just say we started with 12 of unit B, and we want to know how much of unit A we would get. So this would be our equality in this case, which would give us, for this sort of made up problem, these two possible conversion factors that you could use. You obviously would not use both conversion factors in the same problem, otherwise you're undoing your calculation. Now, the way you set this up is a very simple concept of top and bottom, like a fraction. Basically, everything's set up like a fraction. numerator. I think they call it denominator, right? Perhaps. It's not a math class. We don't know. But we got top and bottom there. And the one rule of dimensional analysis is a pretty simple rule. It is opposites cancel. So if you have a unit in a certain location on top and you want to get rid of that unit, you need to put the same unit in the opposite location with your conversion factor on the bottom and vice versa. And they will cancel each other out. So for example, if I were to start this, I would start with what was given to me, 12 unit Bs. And it's really not written as a fraction, but if it helps you, you could throw it over one and make it like a fraction if you want. And what that visually shows me is I could clearly see now my unit B is up on top. That makes my decision really simple when I go to my conversion factors. I need to get rid of unit B. I need to put it in the opposite location. So that is the conversion factor that's going to do that for me. So I like to use parentheses to death. Some people like to use straight lines, railroad tracks, whatever they call it these days. I don't know. But it's all kind of the same deal. I'm going to put my conversion factor like so in there, right? Now, when you set it up like this, which is how you should show your work in most cases here in chemistry, the math is also pretty simplified for you. Anything that's up on top gets multiplied. So whatever you got going on top gets multiplied. Whatever you got on the bottom gets divided. So you don't even have to really think about what I should do. Should I divide? Should I multiply? If it's up on top, you multiply. On bottom, you divide. So when we do that, we're going to multiply the top and then divide by the bottom. But what happens to our unit that's on top and bottom that are the same? They are going to cancel, because ultimately what we are doing is we are taking unit B up on top and dividing it by unit B on the bottom. That equals 1. The same way if we took 4 divided by 4, that would equal 1, right? Or 2 divided by 2, right? Same thing on top and bottom. They divide out. They basically go away. Now we multiply there. We take our 12 and our 5 and we hit equals. We divide by the bottom number and we end up with 30. The unit that we want is up on top by itself and we end up with 30 of unit A. And this is dimensional analysis. This is the way you should show your work in here, especially when it says to show dimensional analysis, or even if it doesn't tell you to show a dimensional analysis, you should probably take a dimensional analysis approach in a lot of cases. Why would you want to do that? Other than the fact that that's the way you should show your work here in chemistry, and they tell you that. A lot of times, it could actually be very beneficial for you. I can't tell you how many people screw up on rearranging formulas. Yes, you don't have to worry about this. All you have to worry about is I need to get rid of those units and end with those units, right? So I just go opposite to cancel. You don't have to worry about, okay, I moved it over here. Am I multiplying or dividing that thing? Oh, it's on top, I multiply. It's on the bottom, I divide. There's actually a lot of formulas. You don't even have to know the formula. You could actually solve the problem taking a dimensional analysis approach by looking at the units. And again, just getting rid of the units you don't need, trying to end with the units you do need. And again, the math is taken care for you. If you set it up this way, everything gets multiplied on top, everything gets divided on the bottom. You know, you don't have to worry too much about a lot of those things. So it's really beneficial, even though a lot of times people don't like to do it. They like to use units anywhere in calculations. You do need to do it if you want full credit, but it also can be very beneficial to do that. You definitely want to set it up so you could clearly see top and bottom, so you know opposites cancel. You don't want to do the stacking method of units where people like to go, 55 miles per hour, and then they do another unit. They're not sure, like, do I like multiply that thing, divide that thing to get rid of it? I'm not really sure. You want to, if you have something like that, by the way, I'll go over here. 55 miles over 1 hour. Again, set it up clearly, miles on top, hours on the bottom. I can't tell you how many people I've given a problem like this to you, and they have to find something like time or something like that, and they end up dividing by the time where they should have been multiplying because they just kind of stack the units and not sure, like, where that unit is. By the way, when you do set it up like this, if you're looking for one unit at the end, it should be by itself up on top, right? If you have 2 units you need to cancel, you can do that as well. So if we had something like, 45.5 inches, and we want to know how many feet that is. Again, we could go our equality that will get us there. 1 foot is 12 inches. Again, that gives us our 2 conversion factors. And it will set up here 45.5 inches. Once again, if it helps you, throw a 1 underneath it. Now my decision making is pretty straightforward. Inches on top, I need to get rid of that. I'm rolling with that one in the opposite location. I'm going to multiply on top. I'm going to divide on the bottom. And we will end up with here the inches canceling. And we end up with here 12. And that gets us 3.79 feet. Now, when we're doing calculations like this and we're using conversion factors that come from equalities, this equality here is an English to English equality or US to US equality. It is considered an exact number, yeah, which means we don't have to worry about it. Here, that has 3 significant figures, and that is why we should end up with 3 significant figures here. Also, the beauty of dimensional analysis is the only math that you do is multiplying and dividing, which means you're always looking at sig figs for your answer, right? So you always know what you should look at when you want your answer. So when you use conversion factors, as we talked about, something like this, where it is 12 inches is like 1 foot, English to English, that is considered an exact sort of number. 100 centimeters in a meter, 1 meter, that is a metric to metric conversion. That is considered exact. When you cross over from English to metric, you do have to take sort of the significant figures into account when you do that. So, you know, if you cross over from English to metric, you do have to look at the sig figs and that conversion factor. There are a few exceptions. The major exception is 1 inch is exactly 2.54 centimeters. So if you're using that, that is still considered an exact conversion, even though you are sort of crossing over when you do that. So for example, if we had something like, I don't know, we'll do like 1 kilometer is equal to 0. I don't know, we'll do 621 is good. 621 miles. Yeah. Miles is English, right? Metric is kilometers, right? Right on your speedometer where it's got kilometers per hour versus miles per hour. So that is a crossover. Here, if we use this as a conversion factor, we should look at the conversion factor, and we would look at the significant figures in this number, and it will contribute to our calculation. So the only time you have to worry about a conversion factor that comes from an equality is if you cross over from English to metric sort of conversion. And usually in a lot of cases like here, there'll be one of the numbers that's a 1 and the other one is an actual number. You want to look at the actual number typically to do so. Now, if we had obviously multiple sort of steps along the way, let's say we did have 2 different units. Let's say we were driving 65.5 miles per hour, right? And we wanted to know maybe how many kilometers per second that would be. Yeah. Why don't you give that a go? You can actually use that conversion I just put on the other page there. 1 kilometer, 0.621 miles. So set it up in dimensional analysis and see what you end up with. Yeah. Okay, so let's take a look. Again, we want to kind of set up dimensional analysis. So with conversions, by the way, there are different ways you could get to the same answer depending on sort of what conversion factor you choose. This is our equality, which would give us, again, our 2 conversion factors here that we could use. Are that miles? I think I missed the 1 there. Over 1 kilometer. So we'll start with our 65 miles, 65.5 miles per hour. When you have anything per something, that's a fraction. The number always stays with the first unit, and it's always 1 of the second unit. Once again, I can't highly emphasize enough that you want to set it up this way. And again, just make it very clear what's on top and what's on the bottom, right? Because that makes it super simple. We basically have 2 conversions we got to do. We got to take the top miles into kilometers, and we got to take the bottom unit of hours into seconds. You can really start with either one first. It doesn't matter. I'm going to start with the miles. I'm going to take it into kilometers because I really have a direct conversion I can do that with right here. Again, miles are on top. Opposites cancel, so I'm going to go with 1 kilometer over 0.621 miles. Again, here at this point, if I stop the calculation, the miles will cancel. I'm in units of kilometers per hour at this point. So I have now successfully got the top part, right? Now I need to work on actually the bottom part. And I know it's the bottom part because I set it up like that. I didn't do like stacked ones. I'm not sure what side the hour is on. So I could clearly see my hours here, and you got a couple of options there. You could go directly to seconds if you want, or if you want to run through a good reminder, right, in 1 minute, there are 60 seconds, right? And in 1 hour, there are 60 minutes. So you could roll that way. You could roll, there's 3,600 seconds in an hour, whichever way you want to roll it. So I'm going to roll through this. I could continue on. And again, because I wrote it like this, I could clearly see my hours are on bottom. So to get rid of my hours, I'm going to put it on top. And I'm going to go 1 hour on top and my 60 minutes on the bottom. Again, opposites cancel. If I stop right at this moment, I'm in kilometers per minute. As close to what I need, but I need seconds. Again, I could clearly see minutes are on the bottom, so opposites cancel. I'm going to put minutes up on top, 1 minute up on top, 60 seconds on the bottom, opposites cancel. The only units left at this point now are kilometers on top and seconds on the bottom. Everything's happy at this point, perhaps. I know exactly everything on top gets multiplied, everything on the bottom gets divided. So in this case, there's not much to multiply up on top since everything's a 1, but just say calculator warning. You could do as many numbers as you like up on top and multiply them. At the end, I would hit equals. Now we come to the bottom where I got multiple numbers. Super common error. People will screw this up, yeah, when they punch it into their calculator because they want to punch all the numbers in at once because that seems like a great idea. Seems like a terrible idea, just so you know, yeah. So if you want to get the right answer, here's what I recommend you doing. If you don't care about it, don't listen. Divide by the first number, 0.621, and then don't be afraid to hit that equals button. Divide by the next number, which is 60, hit the equals button one more time. Divide by the last 60 and hit the equals button, and you will always get the right answer. Now, where people screw up is they decide they want to put all those numbers in at once in their calculator, and maybe they're a little sloppy with the parentheses that should be there, and their calculator does different math because you didn't punch it in correctly. So if you have issues with that, where there's a lot of numbers on the bottom, you got to like divide them, and you get like the wrong answer sometimes, but sometimes the right answer, it's probably the way you're punching in. You're not using parentheses correctly. The way you could avoid that is exactly what I just did there. Basically hit the equal sign after every one you divide. You divide this first one, hit equals, divide the next one, hit equals, divide the next one, and hit equals. And you will always get the right answer, provided you punch the numbers in correctly. And by the way, that right answer in this case is 0.029298622 without some rounding at this point. Kilometers per second. Now we need to look at sig figs, right? So this is exact, don't have to worry about it. That's exact, don't have to worry about it. That is a crossover between metric and English. I do have to worry about it. That's going to contribute 3 significant figures. Do have to worry about the first number, which contributes 3 significant figures. That means right about there is 3 sig figs. And we want to round up 0.0293 kilometers per second. Hope. Any questions on that calculation? So that's a very, very common error that people make, which is they really just try to put in a lot of numbers in at once. And if you aren't really careful with your parentheses, you will get the wrong answer. So you never will get the wrong answer if you just individually hit equals after each one, and you'll be fine. Now on top, it really doesn't matter. You can do as many numbers as you want, but the important part is hit equals at the end and then come to the bottom and divide by everything. Any questions on that there? Okay. Now, a couple other things here, conversion-wise, right? We know metric and prefixes, right? So we have things like nano, as we used in that one experiment, which is 10 to the minus 9. We have things like centi, which is 10 to the minus 2. Maybe we got a little bit of micro action there, or micro, which is 10 to the minus 6. Kilo, which is 10 to the 3. So you do want to make sure you use these correctly, as we might have talked about before. Again, if you had something like nanometers to meters, this is the base unit. This is the prefix unit, right? And when you use that 10 to the minus 9, by the way, that is 1 times 10 to the minus 9 in your calculator if you need to punch it in that way. Again, make sure you use your exponent button. That is how much there is of the base unit to one of the prefix units. And people always get these backwards. They always go like 10 to the minus 9 nanometers is 1 meter. Again, if I had centimeters and meters, one of the prefix unit is 10 to the 2 minus 2 meters in this case, yeah? And again, these are our conversion factors. By the way, to get to the 100 centimeters is 1 meter. You divide both sides by that. And that turns it into 100 centimeters is 1 meter, same conversion. So you could do that as well. Now, it doesn't matter the base unit. If you had 1 nanoliter, that would be 10 to the minus 9 liters, right? And so forth. So they're all kind of the same units. It doesn't matter. The conversion is the same regardless of the units. If you had 1 centigram, that would be 10 to the minus 2 grams. Yeah. Another very common thing that people sometimes do is when they have to go from prefix to prefix, they sometimes run into some issues. So let's just say you had 0.00255 kilograms, and you want to know how many micrograms it is, right? So you're going basically from one prefix to the next, and people always want to try to like sing a song and figure out how many decimal places to move one way or that. I hear there's a song. I don't know the song, to be honest with you, but probably gonna screw up, to be honest with you. And you need to show your work dimensional analysis, so you can't just like move decimals. So the best thing to do is, since you have the conversion in a table like this, to take it back to the base unit and then take it from the base unit to the next prefix unit. So what I mean by that is I could clearly use my kilo conversion to take me back to grams, and then I could use my micro conversion to go from grams to micrograms, right? So going back to the base unit, you're going to be able to find the conversion that you need pretty simply, and you'll be able to get the answer. So if we set that up, 0.00255 kilograms, again, going to do dimensional analysis here. And again, 1 kilogram would be 10 to the 3 grams. So opposites canceling, 1 kilogram on the bottom, 10 to the 3 grams, which is 1 times 10 to the 3. Here, kilograms are going to cancel. I am left with grams at this point. I could clearly see grams are up on top. So I know 1 microgram is 10 to the minus 6 grams. So once again, opposites to cancel. I got to put grams on the bottom and 1 microgram up on top. Grams are going to cancel. I've done dimensional analysis here, so I'm multiplying and dividing, right? So I know the math is taken care of. So I'm going to go 0.00255. I'm going to multiply it by 1 times 10 to the 3. Make sure I put that in scientific notation to my calculator correctly. I am then going to divide basically by the only number on the bottom, which is 10 to the minus 6, which is 1 times 10 to the minus 6. And that's going to give me a giant number with a lot of things. 255, 1, 2, 3, 4 zeros there. Now, in terms of significant figures, this is exact, that's exact. I don't have to worry about it. So we're coming here to 3. And I do have 3, yes. So that is the way I would recommend doing those type of conversions. Again, people oftentimes will screw that up pretty badly by trying to do that. And you can always find those conversions that will take you back, or prefixes that will take you back to the base unit, and you can go from the base unit to the next one. Any questions on that one there? One last thing that people screw up all the time is this. Let's just talk about 12.5 inches cubed to feet cubed, yeah? So if we're going to do this conversion, we could use our 12 inches equals 1 foot, right? So I could set this up and go, again, dimensional analysis, 12.5 inches cubed. Again, I'm going to do 12 inches equals 1 foot. Do I just do one of those? I can't, because that only takes care of one of the inches, right? I actually need to do it not once, not twice, but I need to do it 3 times, yeah? Inches times inches times inches is inches cubed, and they cancel out. Multiplying the top, feet times feet times feet, cubic feet, right? And that gets me here basically 12.5 divided by 12, divided by 12, and divided by 12. Gives me 0.00723 cubic feet. Now, can you set it up like this? 12.5 cubic inches, 1 foot over 12 inches cubed? The answer is absolutely. But in my experience, most of the time, people never live to actually cube the number. They just kind of cube the unit and forget about doing the 12 3 times. So maybe it's better to visually see that, you need to do it 3 times rather than just do it the other way. But it's perfectly fine to do the other way as long as you actually do the calculation correctly. Questions on that there? All right, so that's most of that messed up type stuff. All right, last couple of things here. That is the joyful words right there. So temperature conversions, as we know, we have delta C. No, we have degrees Celsius, degrees Fahrenheit, and Kelvin. And to convert between these two, the temperature in Fahrenheit is equal to 1.8, the temperature in Celsius plus a 32. If you have the Fahrenheit temperature in Celsius is equal to temperature in Fahrenheit minus 32 divided by 1.8. Degrees Celsius is what everybody else uses for temperature. Degrees Fahrenheit is what we use when we take our temperature, right, and stuff like that, and the temperature outside. Now, the one we use the most is really Kelvin, right? And to get the temperature in Kelvin, that is the temperature in Celsius plus 273. The real number is 273.15, but most people drop to 0.15. If you like it, you could keep it, but it's going to round it off anyways. But 273. Obviously, if we have the temperature if we want temperature in Celsius and we have it in Kelvin, we're going to subtract 273. I would say these two are the ones you do the most. Probably not too much Fahrenheit popping in there, but if you do have it in Fahrenheit, you do need to take it to Celsius and then to Kelvin. Most of the time, our temperatures in most formulas in chemistry are going to be needed to be in Kelvin. They're pretty much always going to be needed in Kelvin. And a lot of times we measure the temperature in Celsius. So that Celsius to Kelvin conversion is one we use a lot. And going the opposite way, sometimes the questions ask you for it in Celsius, but you do need to have it in Kelvin. By the way, it is Kelvin. It is not degree Kelvin. We don't use degrees on it. It's just Kelvin. And that is definitely a conversion that you do need to be able to do and know. Lastly here, density. Right? Density is mass divided by volume. Common units of density are grams per milliliter, or grams per cubic centimeter. A reminder that 1 milliliter is the same as 1 cubic centimeter. That is a volume, by the way. By the way, you could get a volume a couple of different ways. You could simply just take a reading, right, off of an equipment. If you have a solid, you can measure the length times the width times the height. And if you measure each of those in centimeters, you will end up with cubic centimeters, and that is a volume. So each of these are length measurements. When you take 3 length measurements and multiply them together, you will get a volume in this case, right? Heck, if you're in medicine, 1 cc as well is a volume as well. That's a cubic centimeter. By the way, 1,000 milliliters equals 1 liter is a super common conversion we use for volume, right? Along the way. These are the typical units for solids and liquids. When we get into the gas chapter, density is oftentimes given in grams per liter for gases. It's very commonly given. That is an equation that you could rearrange. D is equal to M divided by V. Volume would be M divided by D. And mass would be volume times density. Sometimes people remember this by the DMV triangle, right? Everybody loves the DMV. There you go. Density is mass divided by volume, right? Volume is mass divided by density, and mass is volume times density. If something is more dense than liquid water, for example, it will sink, right? If something is less dense, it will float. If you have two liquids that have different densities and you put them into like a graduated cylinder, you'll get some separation, right? That happens. And if you drop something solid in there and it sits right about there, that means that solid is less dense than those guys layers and more dense. Sorry, I said the opposite. More dense than the top layers and less dense than the bottom layers there as you go through there. One of the most common ways that we could get volume besides those two ways that happens a lot with density is volume by displacement, right? So volume by displacement. That is when you take a cylinder that has some type of liquid in it, like water. You take some type of solid object and dunk it in. That will cause the liquid level there to rise to a final volume. If you take the difference in the volume here, that will give you the volume of the object, which is the final volume minus the initial volume, right? The density of liquid water, if you ever need to use it in a problem, is typically 1 gram per milliliter, is typically the value that you use for the density of water. By the way, as you may know or may remember, density does change with temperature. So as the temperature changes, so does the density. One of the most common things, right, is the solid state of substances are usually more dense than the liquid state. The one exception where the solid state is not as dense as the liquid state is what thing? Water, right? Ice cubes, right? So ice is less dense than liquid water. And that is because when it comes together in the ice form, the water molecules don't have enough energy to get super close to each other. And it bloats a lot of empty space between the water molecules. And what that does, if you think about density, is it makes the volume of ice a lot larger, and that's going to lower the density value because you're dividing by a larger number. And that's different than in the liquid form. In liquid form, they have enough energy to get kind of a little bit closer to each other, and it doesn't get as bloated that happens in that case, right? And that's what happens, right, when you put like a soda or something in your freezer and forget about it, bottom of the can, right, starts to swell out. That's because all the water in there, the ice starts to expand. It's got nowhere to go, pushes out the aluminum, and now your little can just starts wobbling around. Any questions on that there?